All right, welcome. Today, we're diving into the world of advanced manufacturing to see how predictive science is totally shaking up one of the oldest technologies around. We're talking about a shift from an old school craft, based on trial and error, to a full blown science that can literally design materials on demand. Let's get right into it. So, I want to kick things off with a question for you. What's the one thing that connects the deepest trenches in our oceans with the cutting edge of space exploration? The answer is, quite literally, what holds our entire modern world together. Yep, it's welding. From massive infrastructure projects to the sleekest rockets. We can't do without it. But here's the crazy part. While we're using it to build the future, the methods we use to guarantee a good weld, well, they've been kind of stuck in the past, relying on little more than trial and error. And that old school trial and error approach, it's created a massive billion-dollar bottleneck for manufacturing and innovation. Let's really dig into why that is. First, just try to wrap your head around the sheer complexity here. There are over 70 different official ways to weld something. You've got everything from simple arc welding to super high-tech laser and electron beam methods, and every single one is its own little universe. Okay, now take those 70-plus processes and combine them with the hundreds of different metals and alloys we use today. All kinds of steels, titaniums, superalloys, you name it. The number of possible combinations, it's just absolutely staggering. So to manage all this chaos, the industry came up with something called a Welding Procedure Specification, or a WPS. And honestly, the best way to think of it is as a super strict, really detailed cookbook. You follow the recipe to the letter, and you get a certified weld. But what happens if you want to change just one tiny ingredient? Well, that's the whole problem, right? Creating one of these recipes is incredibly slow and unbelievably expensive. It kills innovation, because if you have a new material or a new design, you have to start that whole painful trial and error process all over again. And since every company keeps the recipe secret, the industry just ends up reinventing the wheel over and over and over. But what if we could just throw that cookbook in the trash and replace it with fundamental science? Well, that's the whole idea behind a revolution that's being called process-based quality. So instead of just testing the final weld and hoping for the best, this new approach uses these powerful physics-based computer models to look at everything at once: the design, the materials, the process itself, and how it's going to perform. The goal is to predict the outcome before you even strike a single spark. And what's so great about this slide is this quote from the author of the paper we're looking at, S.S. Babu. He's asking the big question here. Can we finally find a way to qualify parts scientifically, with minimal trial and error? This is the exact problem that process-based quality sets out to solve. And this chart just lays out the whole shift perfectly. We're moving away from being reactive, testing and fixing, to being predictive and getting it right the first time. We're swapping out that rigid old recipe for a flexible scientific framework that can adapt to anything we throw at it. So how does this actually work in practice? Well, it all comes down to this really cool digital feedback loop that has 3 key steps happening all at the same time. First, you model. You run these powerful computer simulations that predict exactly how the material is going to behave, what its internal structure will look like, where the stresses will be. Then you make. As the real physical weld is happening, sensors are recording every single variable you can imagine. And at the very same time, you measure. You have sensors right there in the action, watching the material's real-time response, tracking things like temperature and strain. All of this data gets fed right back into the model, making it smarter and more accurate with every pass. Okay, that all sounds fantastic in theory, right? But the real question is, does it actually hold up in the real world? Let's take a look at the proof, and we'll start with a little story I like to call the tale of 2 steels. So for our first case study, researchers looked at 2 different steel welds. They were almost identical in every way, except for one tiny little difference in their chemistry. And get this, the weld that had just a tiny bit more aluminum in it formed a completely different internal crystal structure. It was this rigid, column-like network. The other one, it formed that classic, more uniform structure you expect from steel. So this tiny change in the recipe led to a massive difference in the material's basic properties. So here's the knockout punch. The amazing part is that these new computer models predicted those completely different outcomes perfectly, Without a single physical test, the software knew exactly how each steel would behave, simply based on the fundamental laws of physics and chemistry. Incredible. That is seriously impressive. But it leads to an even bigger, even crazier question. If we can predict a material structure, can we flip the script? Can we actually use software to design a material's internal structure on purpose from the ground up? This is where it gets truly mind-bending. Using a 3D printer, researchers made two little cubes out of the exact same metal powder. For the first cube, they programmed the software to control the printer's laser in a way that created what's called a columnar grain structure. Think of it like a tight bundle of straws, all pointing the same way. For the second cube, they used a different laser pattern to create an equiact structure, where the grains are all jumbled up and pointing in random directions. I mean, just let that sink in for a second. The exact same metal, on the exact same machine, produced two materials with totally different internal structures and, because of that, totally different properties, all controlled by software. This is basically the holy grail of material science, telling a machine what kind of microstructure you want and having it make it for you. So you see, this isn't just about making welding better. This is about a fundamental shift in how we make everything. We are literally forging a new future for manufacturing. And what does that future look like? Well, it means smarter, much more reliable 3D printing for one. It means we can custom design new materials with the exact properties we need for a specific job. Innovation cycles that used to take years, they could be crushed down into just weeks. And of course, it means we can build lighter, stronger, and more efficient parts for everything, from our cars to our power plants. You know, what's really amazing is just how fast this is all moving. Back in the year 2000, the American Welding Society set this huge 40-year goal to make this kind of revolution happen. But thanks to huge leaps in computing power, we're getting there way, way ahead of schedule. Today, we're already designing materials with software. The future, where we qualify parts almost entirely virtually, is right around the corner. And that leaves us with one final fascinating thought. For all of human history, we've basically been limited by the materials we could find lying around. But now, we're standing on the edge of being able to design them from the ground up, literally atom by atom. So the only question left is, what are we going to build next?